Hello. Am I audible now? Okay. Okay. So, hi everyone. Welcome to the live section of this course, which is Quantum Transport. So, I'm Gitanjali. I'm a based scholar from IT Delhi, and I'm the TA for this course. So, in the last session, if you recall, so we were going through what happens to the charge carrier transport whenever we have a quantum diffusive region. So in quantum diffusive, we looked at the concepts such as weak localization, weak anti-localization, and what are the concepts associated with it. So these are some of the concept for the case where we have quantum diffusive reason. For today's session, we will cover what happens when we have a quantum ballistic reason. So, if the device is such that it's satisfying the quantum ballistic condition, then what happens to the transport and whether there is any concept similar to the diffusive or whether there is any other concept that is related to that happens in the quantum ballistic reason. So we will go through in brief the concept that has been covered in the class for week 6. Then we'll try to solve the problems related to week 6 as well as week 5. You have doubts in week 5 assignment. Okay. You can ask your doubt. I will try to clarify the concept, but not the answer. So let just ask me whether what is the doubt you have. I will try my best to clarify that. Then we'll move on. Can you tell me the question number? Then let me see. Give me a few minutes so that I can log into the portal. Just let me know the question number. I will try to clarify the concept, then you can just guess what do you think the possible answer for that question. Give me 2 minutes. So it's loading. Question number 1 and 2. Okay. Quantum transport. In 1 and 2, mm, is the solution has been released for week 5? Okay. Yes, the solution is released. Okay. Question number one. I wrote first answer as transport is good. Okay, so you have doubt for question number one. You want zero point 0.5, so you have corrected only one option. And so for that, you want the zero point 0.5 score for that. Okay, noted. For second question, they asked only in forward direction, so I mean 2 is correct. In the quantum diffusive regime, the return probability for an electron is times times the probability to propagate the forward direction. Okay. For zero point 0.5 score, I think only the team can address this question. So, uh, give me some time. I will write to them today only. I will write to them about your query regarding zero point 0.5 score, or I will tell them that no one is responding in the Q&A. So I think just give me some time. I will write to them. They will definitely give some answer to this. And for your second question, return probability is dash times the probability to propagate in the forward direction. So for that, if you recall, it is, I think, if I go through the concept, it is 4 times 5 by 50. Four five by 50. Have you raised your query for second question in the Q&A? If yes, then let me ask about this also. Okay, so if you have raised all your queries, okay, no one is responding. Okay, then I will assure you by today I will write to them regarding your query. I will tell them that the students have raised the query about the assignment in the Q&A, and I will write to them. I will write to them, and by tomorrow maybe, or by tomorrow, or by day after tomorrow, I will get a response. So I think mm, in that way, it's possible to solve your queries about the assignment. So give me some time. By today, I will write to them for your queries, and no response in the week for your question in assignment. Week 5. Uh, According to me, I think for second question, the answer should be whatever given in the site, like it's 4. Because it's like, if you recall, um, for one path, for one time reverse path. So the phase, the probability will be like um, it is 4 times t square, right? For forward direction, it is 4 times t square, the probability or summation of t square. This is for forward direction, but it's given the returning probability. So 4, again, forward is 4, then backward is 4. So I think it's 4 times. It should be 4 times. All about phase. Yeah, I think uh, okay. So the question is, in the quantum diffusive regime, what is the return probability for electron? Is dash times the probability to propagate in the forward direction. So for, okay, I got it now. Uh, mm, it's actually directly whatever solve in the weekly concepts. So for to find out the probability of forward direction, so if you recall, probability is nothing but square of the wave function, right? So and forward is like to go from A to C. Sorry, let me take a page. To go from A to C, this is the forward this is the way we can calculate the what is the probability of uh, finding the particle here when it comes from A. So this we have calculated that the particle can take multiple paths. So it can take path 1, part 2, part 3, or part 4. And find out that the probability you can write it as from A to C. It is nothing but more. So what is the wave function here? So wave function would be summation of psi I from 1 to whatever the paths they have. This is mod square. So this we have already seen, and this we have calculated here also. We have a marker here. Okay, so this is the probability for, if you see here, this is the forward probability of forward propagating wave. So PC we have calculated is summation of Tj square, right? So if you look at this equation, it is summation of Tj square. This is clear? Is this clear? This is the probability that the particle will be found at point C when it starts the journey from point A. Now for the return probability, this we have taken what is the probability of getting the particle at the point A when it starts from point A only. So this also we have calculated by taking the time reverse path, and we say that the phase are same in the time reverse path because there is no magnetic field. So if there is no magnetic field, there won't be any phase difference. So the geometrical phase difference, they are more and less same. So that is why we have taken 0 here. From that, you have calculated that the probability of return, it is 4 times of summation of Ti square. right? And this summation of ti square is nothing but probability of C, this one, right? So this is the probability of forward propagating wave. So that is why the answer would be the same. It is 4 times the probability propagate in the forward direction. So is this clear? Question number 2. Okay, so if you see, look at the assignment. So these are, they totally cover the concept, whatever given in that week. So go through the concept in detail. So try to understand the concept that has been taught in week. And also you can revise the session or the concept that I also tell in the lab session. So I think that will be enough for you to solve the assignment. If not, and one thing is about your query, I will write to them by today and let them know that they have doubts in the assignment so that it can be solved in the earliest. Okay, don't worry. So, just it's just a matter of time. I will. It's like I think they are not aware of the question that has been raised in the Q&A. So just give me today's time. So I will let them know that you have this much doubts in the assignment, and also whatever the queries you have, write them explicitly, like in the Q&A part. So write them explicitly that I have doubt in question number this, and also attach your solution. Like if it is a numerical one, then try to attach your solution, how you have calculated the answer that you are getting. If it is a conceptual one, no need to attach the anything. Just let them know that you are getting this and you want the explanation for this. Okay. In that way, I think it would be easy for them to track and also address your query. Okay, so do you have any other doubt for the assignment of week 5? If not, we'll see the concept in brief for week 6, then we'll try to solve the questions. Okay, so let us start our session. So for week 6, so we were basically in the we saw what happens to the device when we consider the quantum ballistic reason. So for one of the example of the transport in quantum ballistic reason is the quantum point contacts. So we have seen two types of contact. One is quantum point contact for the 2D when we have a semiconductor 2D electron gas. And one other thing we have is the metal. This is for atomic point contact. And the difference is, if you recall, the difference is mainly due to the Fermi wave vector, which is very small for the metal, and for semiconductor it is 100 times larger than the Fermi wave vector of the metal. So because of this difference, they have different terminology for and different types of different point contact for to see the ballistic transport regime. So we'll see in brief how why the metals show different types, different type of point contact. So for now, let us see the quantum point contact. So this is nothing but this is a, if we recall, what is a quantum point contact? So this is a 1D ballistic. Constriction. So by ballistic, we what do we mean by ballistic? So if we recall, so for ballistic, we need to have the Fermi vector lambda f Fermi wavelength. Sorry, Fermi wavelength should be in the order of the device length, and this should be much less than the mean free path of the elastic collision and the phase coherence length. So this is for the quantum ballistic reason. So this we have already seen in week 1. This should be the condition. And so to see the quantum point contact, that is the 1D ballistic constriction, we need to have a opening, that is which is the width opening of the constriction. It or we say this is the width of the constriction. It should be comparable to the Fermi wavelength to see the 1D ballistic transport, 1D quantum ballistic transport is. So this is, and because this is a 1D constriction, the transport will be in one dimension. Transport is 1D. And where do we see this kind of effect? We visually see this kind of 1D quantum ballistic transport in a 2D semiconductor heterostructure. We'll see that the 2D semiconductor heterostructure, it's not only the case where we see this quantum ballistic construction. We have other like metal and other material where we also see the same kind of effect. So this is one of the case where we can see the 1D ballistic transport, quantum ballistic transport. And these are nothing but, these are some of the definition that I am going through. So quantum point contact, these are short, narrow channel defined in the 2D electron gas of a semiconductor heterojunction. Okay. And we see that as we vary the width of the system, then the subbands that is present in the system, they will pass one by one through the Fermi energy. And because of this, we will see a jump, a step-like variation of resistance or conductance. Okay, so we'll see in brief about this. Uh, it is 1D ballistic. No need to write it down. Just try to go through the concept. I will upload the file in the drive. Okay. For now, you can write it down also. No problem. But if not required, you can also just try to just go through the concept, and I will upload the files in the Google Drive. There you can see the questions, also the whatever I'm writing in the worksheet. So these are quantum point contests. These are 1D ballistic construction. By ballistic, we means that the Fermi wavelength of the charge carrier should be in the order of the device length, and the mean free path of the collision, elastic collision or the phase coherence length, they should be much larger than this device length or the Fermi wavelength, so that the scattering can be minimized in the device, and we'll see the quantized effect in conductance as well as in resistance. So if you recall, in diffusive transport, we have seen weak localization because there is a coherent backscattering of charge carrier, and without the magnetic field, we see that there is a non-zero probability that the electron will return back to its original position. That means if it is returning back, there will be a lowering of conductance, and there will be a increase in resistance. So this is because of the coherent backscattering. But when we consider the ballistic one, so this is the transport regime where we can suppress the scattering. And this is the scattering is suppressed because the mean free path is much larger than the Fermi wavelength or the device length. Because the mean free path is very large, then there won't be any scattering, right? So that is why we say this is a ballistic transport regime where the scattering can be minimized, and this minimization is because of larger value of the mean free path, which is much larger than the Fermi wavelength or the device length. Okay. And the transport through the quantum point contact, it is 1D. And we'll see one of the example where we have considered a 2D semiconductor heterostructure to see what is happening around this quantum point contact region. And we saw that, in brief, we saw that there is a step-like variation of resistance and conductance, which we have also seen in the quantum Hall effect. Okay. Okay, so this is about the definition of quantum point contact. So if you have no gate voltage, so we have a point contact. So we have a 2D electron gas, then we have made a constriction around it. And if we don't apply any gate voltage through this constriction, then what will be the transport? The transport will be free in the XY plane. So XY plane, whatever the energy levels of this 2D electron gas, these electrons will travel, they will transport freely in the XY plane. Now, when we apply a gate voltage, so what will happen? So we apply a gate voltage. So that means there will be a electric field or a barrier that will be created in the y direction. So we are considering this is x, and is my whatever I'm drawing on the worksheet, is it visible to you, or you want me to draw it in a bigger manner? Let me. So we have a 2D gas, 2D electron semiconductor, then we have made quantum point contacts here. And this is y direction, this is x, and the z direction is where the transport is arrested. Like there is no transport along the z direction. Okay, so without the gate voltage, they will move freely, and the energy will be h got k square by 2m. So energy without the gate voltage, this will be h got kx square by 2m plus h got ky square by 2m. And if you recall, we have equated to n plus half h cut omega. From that, we have seen also the quantization, Landau level, and other concepts. For this one, we are now restricting the carrier transport in some of the region around the quantum point contact. So here, if you see, there is a potential barrier that will be created by this point contact in the y direction. So that means even if the transport is free in the x direction, in the y direction, we will say that there is a confinement effect because of this applied voltage along the quantum point contact. And we can approximate it as a energy as a nearly parabolic one. For simplicity, we are taking nearly parabolic to see what is happening in the first case. And z direction, it is already arrested. So for that, Now this is the expression without the gate voltage. Now we have a gate voltage applied along the quantum point contact. It. Okay, your my writing is not clear. So let me take. Is the color of the writing is fine? Or let me write in the black one then. I think that would be the best choice. Okay, if color is fine. Okay, so let me write in a big font size. So now when we apply a gate voltage, what will happen? So this y direction, it becomes, because there is a confinement effect, now we will see quantized energy level for y direction, but the x direction, it remains unchanged. Okay, so y direction there will be a contest, and in the x direction the particle will move freely, which was before, which was what it has before also. And because of this energy quantization, this will create a series of bands. So this will create a series of band, and the energy spacing between these bands is it is in the order of some order of milli electron volt. Okay, and to calculate what is the number of modes along this constriction direction or along the y direction where the confinement effect is happening, you can use this formula. So number of modes supported along the constriction direction. If we recall, it is given by 2 W by lambda F. So W is the width of this constriction, lambda F is the Fermi wavelength that you need to calculate by taking the 2D electron gas relation. Okay, so this is the overall effect. Now let us see what will happen to the energy level and how we can calculate how this number of modes are getting affected by the gate voltage. W, it is the width, or you can say if is in the picture, it is the width W. What is the width of this quantum point contact? Is in the y direction, it is W. Width, the constriction. Okay. So now what will happen whenever the electron, when it tries to enter the quantum point contact region, then we'll see a confinement effect because of this gate voltage. But once it cross the channel region or the constriction region, then in that case, the whatever the modes that is supported in the constrictor region, they will interact with the energy level of this 2D electron gas. So for that, uh, let us see. So that means the number of modes. So we have a constriction here, right? And the number of modes that is available for transport along this constriction region. So this depends on the gate voltage applied along the y direction or along the constriction. So what will happen? So in short, what we have seen that, so when we increase the negative voltage. So this will, so we have a, so in the construction direction, if you recall, we have a parabolic confinement, right? So when we increase the negative voltage, this parabola, they gradually shift along this vertical direction. So the base of this parabola will gradually shift upward. So because of this, what will happen? The levels, the energy supported energy level, they will pass the Fermi level one by one. And because of that, so because it is in the y direction, it is n plus half h cut omega c, there is a confinement. And now we are increasing the negative gate voltage. So because the energy levels are crossing one by one, so we'll see a step-like variation of resistance or conductance when we increase the negative gate voltage. So this is one of the observation that there will be a step-like variation when we increase the negative gate voltage. So the effect is step-like variation of conductance or resistance. The second effect is that when we increase the negative gate voltage, so the spacing between the levels, it also increases. This is the second effect. It increases. And because of that, the same effect is observed, like we'll see a step-like variation of the conductance as well as the resistance whenever we increase the gate voltage. And also also one of the effect is that there will be a step-like variation. This is one effect, and the conductance will gradually decrease because the energy levels are skipping one by one. So because of that, we'll see a decrease in the conductance, which we have also seen in the quantum Hall effect. If we recall, when we increase the magnetic field, then the Landau levels below the Fermi level, they pass through this Fermi level, and because of that, we see that there is a the number of occupied Landau level decreases, and because of that, the conductance also decreases. The similar effect is happening here. When we increase the gate voltage, we will first see a step-like variation of conductance resistance, and also we'll see that the conductance and the conductance will gradually decrease and the resistance will gradually increase because of this negative gate voltage. And the expression for conductance and the resistance, it is similar to what we have seen in quantum Hall effect. So without any degeneracy, we can write the conductance as E square by H into N. N is which is the number of reflectionless channel. If you recall, in the quantum Hall effect, this is the number of the Landau level. For here, we have number of modes or number of reflectionless channel. But if we have a spin degeneracy or any other degeneracy, then we can multiply the degeneracy factor here. For spin degeneracy, we have 2 factor here. And if we have spin and valley, then we will have a factor of 4 here. Okay, so this is the Landover formalism for conduction of the transport for the transport in 1D. Okay. So the to summarize, I will summarize whatever I was talking about. So when we increase the negative gate voltage across this construction, so this will lead to a decrease in the number of channels or number of modes that is available along the 2 and 4. Okay. 2 and 4, what I mean is that without any degeneracy, we have E square by H into N. But let's say we have a spin degeneracy, which we often see without the magnetic field. So when B is 0, then there is for fermions, then there is two spin, spin plus half, spin minus half. So this spin plus half and this spin minus half, they have the same energy and they occupy the same energy level. So that is why we say that the conductance of this level is now 2 E square by H into N. But this is for spin degeneracy. But consider a case like you have a bilayer graphene. So for bilayer graphene, because of the symmetry of this graphene lattice, so there is a valid degeneracy in addition to the spin degeneracy. We have spin degeneracy also, we have a valid degeneracy also. Okay, this spin degeneracy correspond to factor of 2. This value also correspond to a factor of 2. So two values have the same energy and also two spin also have the same energy. So that is why for the bilayer graphene, we say that the conductance is now 4 times E square by H without the magnetic field. Okay, so this is what I was telling earlier. For spin distance, we have 2. If we have both spin and valley, it is 4. So the overall effect of the negative voltage is that they will decrease the number of channels that is available for transport along this construction. So if number of channel is decreasing, that means conductance will decrease and the resistance will also increase. And this decrease in conductance, they don't happen randomly. So they changes in a step-like manner because of this quantized effect, because of this confinement effect. Because of the confinement, we will see discrete energy level along the y direction. So that is why when we change the voltage, the conductance changes in a step-like manner. Okay. So this is the overall effect of the gate voltage. Okay, so let us see what we have in the next case. In the next part, we have seen uh, this is what I am talking about, spin degeneracy and valid degeneracy. And after that, we have seen the conductance in the metal. So this is for the 2D electron gas for the semiconductor heterostructure. For metal, we have a similar concept, but it is atomic point contact. So conductance, quantization in metals. So as I said earlier, so this conductance quantization, these are not particularly a case that we have seen in 2D electron gas. We can see the similar effect in other material like a metal. So the point is that in what dimension we can see the same effect for the metal what we have seen in the semiconductor. So if we recall for metals to see the quantized conductance, the lambda f should be in the order of the dimension of the conductor or the length of this dimension. This is the ballistic condition, which we have seen for the semiconductor also. But one thing is that for metal, if we recall the charge density N by B, it is very, very high. And lambda F, this is the relation. You can write the lambda F as 2 pi by kf. And for metal, for the 3D case, we can write 2 pi kf is 3 pi square 1 by 3 V by N. Or this we can write it as 2 pi 3 pi square ns. Ns or n, just n. This is the charge density or the number density. So this number density for the metal, it is very, very high. Because of that, we'll see that the lambda f for the metal, it is very, very small as compared to the semiconductor. 2D electron gas. Okay. So, and we'll calculate one of the case where we can see that the lambda f for the metal, it is in the order of nanometer, some fraction of nanometer. Okay. So that means, what does this imply? The lambda f, it is in the order of atomic dimension. It is in the order of angstrom. So that is why if you want to see the same ballistic transport for the metal, we need to consider a atomic point contact. Okay, so we need to consider a atomic point contact for the metal scale. For the metal where the width of this construction should be in the order of atomic dimension. Okay, so this is the overall concept for the how we can see the same quantization for the metal case. Now, if you take it, mm, so if you compare the transport in semiconductor as well as the metal. So if you take the same dimension for both the case, in one case we'll see quantization, in other case we won't see quantization if we consider the same device length. But if we decrease the device length or the construction width for the metal case to atomic dimension, then we will be able to see the same quantized conductance for the metal case. Okay. Okay, so let us move to our next part. In the second, towards the second lecture, we have tried to calculate the different regime where the current, where we calculated the current, and we see what are the regime where it satisfies the Ohm's law, and how to calculate the power dissipation. So let us see the first case, that is how we can calculate the current from the transmission. So let us say we have a source and drain. So this is the source part, and we have a drain. This is the top level where this is the electrostatics chemical potential. For the source part, UL is the top point of the conduction band. For the source part, this is for the top part for the drain region, and this is the electrostatic potential of the drain side. So for this one, if you want to calculate what is the current IL, where the transport is happening from the left electrode to the right electrode, that is we are going from source to drain. So for this we can write IL is 2E 0 to infinity f of, give me 1 minute. So for this, we have expression like 2e, the Fermi Dirac distribution, mu group velocity, Tk, transmission coefficient, and what is the allowed number of states. So this is in the K space, but we are more interested what is happening in the energy space because we are varying the voltage, right? So we are directly varying the energy of this source and drain. So we want to see what is happening in the energy space. So for that, we can try to calculate the try to relate dk with de, and we can substitute dk with de to see the relation. So if we recall the group velocity, this is the user definition. Group velocity is given by d omega by dk. We want to relate dk with d. So let us divide the numerator by de, also the denominator by d. So in the we want to calculate dk by de. So that means dk by de, it is d omega by de 1 by v, and d omega by de, it is 1 by h cot, right? 1 by h cot v. So this is the relation. So we can put it here. C IL is 2e 0 to infinity f of epsilon, or we can write it as E mu L V E T E, and dk is 1 by d by h got v. The v will cancel with the v here, and we are left with IL is 2e by h 0 to infinity f of E mu L T D. This is for the right propagating wave. For the left one, we have the same case, but the sign will be changed because it is moving in the backward direction. H cot, this H cot will cancel the 2 pi here. So that is why I have written only H. Okay. So this H cot will cancel the 2 pi. So for IR, we have the same case, and we also can change the limit also, because only the energy level from UL onwards, they will participate in the transport. So no need to take it from 0. For the left side, you can take it from UL, and for the right side, we can start from UR. So this is D. And you can calculate the net current. Okay, so H is coming because if you recall, there is a there is a H cut here, and I have put H by V here, and there is a 2 pi over here. This 2 pi and this H cut. H cut is H by 2 pi, right? So this 2 pi will cancel with one of the 2 pi, and that is how we can get the H here. So this is the current. Now the you can write total current as IL plus IR, which I think you can. This is just a final expression without any modification. Now let us see what happens for the different case. If you have a small bias or if you have a large bias or other case. So for the last bias, what will happen is that for the when the bias is less, then there won't be any backward propagating wave. So you can write the current will be equal to the IL. Okay, so whatever expression we have it here, for large bias, we have the same expression. So that means there is no voltage, there is no relation like V is IR. So there is no ohmic relation here for the large bias case. Now if we have a small bias, so in that case, uh, for small bias, we can write the chemical potential because the gap is very, very less. So we can write mu L as mu plus EV by 2 and mu R, we can write it as some mu minus EV by 2. From this, we can expand the Fermi function. Okay. So if you recall the I think, okay, f of E in the I total current, we have an expression like f of E mu L minus f of E minus mu R. We have an expression like this. Now we can expand this. So mu L is mu plus EB by 2 and mu R is this is mu minus EV by 2. So we can Taylor expand it to first order because so for this case, when you have a expansion like this where the EV term is very small, right? So when you have a expression like this where this term is very less, you can write it as f of E mu plus what is the small term that is added here? So EV by 2 and delta F by dou E. This is the expansion up to Taylor expansion up to first order. The same expression you can write it for the second case. So this is f of E mu minus, because there is a minus term here, so we will get a minus EV by 2. I think better if I write it down. So minus EV by 2 dou F E mu by dou. So in overall, this will cancel and these two terms will give EV dou F E mu by dou. Okay, this is for the small bias case. For now, we can write the net current, which is 2E by H UL to infinity EV dou F by dou E D of E D. So we can see a voltage term here. So that means we can write so there is a relation of ohmic like relation here for the small bias case. So I net is directly proportional to V, or we can say that the Ohm's law, it is valid when we have a small bias. Okay. Now for the second case, what we have a low temperature limit. What happens when we have a low temperature limit? So for this, what we can see that the Fermi function, it is a step like, it would show a step like function. So that means we have seen you can write the current as 2E by H. You are 2 mu L T E. And in the high temperature limit, if we recall, for high temperature, the Fermi function is, it is, these are highly localized, they highly pick a sharp value around the Fermi energy level because it's a very, very low temperature. So for this case, the partial derivative we have, you can write it as some delta function because it's showing a peak value around the Fermi function. And for the conductance, this you can write it as dou E square by H UL to infinity, dou F by dou E, which is delta mu dE dE. And the limit will give T mu. Okay, so for very low temperature, it doesn't care about what is happening below the Fermi level. So it picks the transmission around this electrostatic chemical potential. Okay, what is T? It is the transmission. What is the transmission coefficient? Like, it's like the probability. So what is, how much injected carrier is getting towards the forward direction. So this is the transmission coefficient. Okay. Okay. This is about the different cases that we have seen. Now we'll see. We have considered that this transport is happening in the quantum ballistic region and there is no scattering. But here we have seen that even though there is no scattering, we are getting a conductance, which is a finite value. So conductance is finite means we will have a finite resistance. That means we can say that even though there is no scattering is happening, we are getting a finite resistance. So now you can say there is some scattering happening in the quantum ballistic regime also, but it is not the case. In quantum ballistic regime, there is no scattering, but what is happening here is that, so in short, what is happening that if you have a constriction, so whatever channel is flowing through this constriction, these are reflectionless, there is no backscattering. But after this constriction, this channel, it will flow in this 2D electron gas semiconductor. So that means this 1D channel, it will interact with this 2D electron gas. Because of this interaction, we will see there is a finite resistance because of this interaction. Okay, so whatever resistance is happening, it is because of the interaction between this 1D channel between with the 2D electron gas. Once it crosses the channel, it will interact in the energy levels of this 2D electron gas, and because they have different energy levels. So in 1D, in the channel, there is no scattering happening. But when it enters this 2D electron gas channel, then there will be a scattering. And because of that scattering, we'll see a finite resistance, which we also call it as a contact resistance. We'll see the expression in detail. Okay. So let us see. So we have a source side and we have a drain side. And we're considering these are black box. We don't know what is inside this, but we know this is the top of, this is the electrostatic potential of the source and this is the drain. Okay. Now, when the electron travels from this source to drain, and we assume that there is no dissipation in energy in the channel. So for that case, let's say the energy is between mu L to mu R. Let's say this is the case. And if you recall, the energy that is left behind the source point, we can write it as mu L minus E. And for the drain side, we can write it as this is E minus mu R. So that means the total energy that is dissipated at the source and drain electrode, it is summation of this, which is E VSD. VSD is it is the voltage applied between the source and drain side. So this energy dissipation, it is independent of this energy of the electron. So to calculate what is the power or what is the resistance that we'll see when this 1D channel meets the 2D electron gas. So the expression for power, it is, you can write it as total energy that is dissipated and what is the time taken to travel from source to drain. We don't know the expression for this tau. So let us see how we can calculate it. So for that, we can take the expression for the current. So for current, for the small current, di from source to drain, you can write it as di is conductance time dv. And conductance is, this is 2 e square by h into n into dv. And we can rewrite this 2 e square by h or E dV. So I have taken one E out here. So I have kept it here. E dV is nothing but D, the small change in energy. So we have the expression for the current. It is 2 En by H D. And this expression, it is similar to the expression of the current, which has the form E by tau. This is another expression for the current. So current is charge by time. And if we equate it to here, we found that tau is, it is, or let's say 1 by tau. That's what we want. 1 by tau is 2 NDE over H. Okay. So we can put 1 by tau to the power expression. So power dP is total energy deposited by time, which is 2 ND. So the total power you can calculate by taking the integration U to UL to E N VST by H into D. These are all constant, these are fixed, and these can be controlled by us. So that means power, you can write it as 2 any mm, BST by H and mu L minus mu R. Mu L minus mu R, this is EVST. So that means the expression for power that is dissipated, this is given by V square ST by H 2E square N. And this expression is similar to V square by R. Okay, so that means the contact resistance, this has the form H by 2E square 1 by N. So I hope you are following whatever I'm trying to say. So this is the contact resistance. So even if we don't have any dissipation, so if you, let's say we have a schematic here. So this is the quantum point contact region. This is the source. This source. This is drain. And this is the quantum point contact that we have created. So even though we don't, so this supports 1D channel, right? 1D dispersion reflectionless channel. And even though we don't have any dispersion in this 1D dispersionless, 1D quantum point contacts, we see a finite resistance during the transport because when the charge carrier, when this 1D mode, when it enters the 2D electron gas, so this to this bulk part and the 2D bulk part, uh, once again, which one of the case you want to repeat? Up to this part, whether it is, let me know whether it is clear or not. You have followed the contact resistance, right? DI here or before that? This one. I think this is where I've started from current or before that. You want to repeat me from here or the next part here? Okay. From in this part, what we have tried to calculate is that we try to calculate what is the power dissipated when the electrons travel from the source side to the drain side, because we are seeing finite resistance, right? So if there is a finite resistance, then there should be a expression for that. So we are trying to calculate what is the expression for this resistance. So for that, we can start from the power expression. So power, it is given by the energy over time. So total energy dissipated is EVST, which is mu L minus mu R. And this is tau is the time which is taken from the transport from source to drain. So in schematic, so we are considering this one. This is source side, this one is drain side. And the total energy dissipated from source to drain is EVST, and we're taking, this is the time tau it is taking to go from source to drain. So to calculate tau, what we are doing, so we are taking the help from the current expression. So current DI, you can write it as GdV, right? So this you can write it as GdV whenever you have a ohmic reason, right? So ohmic region is valid when we have a small bias. So we are considering a small bias case. So we can write di as conductance time TV. And conductance, this is a expression of quantized value, which is 2 e square by h into n. This we have seen earlier. So this is the expression for G, and this is the usual expression for the dV. Now what I have done, I have taken one E from this part and I put it here. And we can write EdV as the energy change dE. Okay. So dI, now we have dI is 2En dE by H. So now we can equate it to the expression of the current. So current you can also write it as dq by dt, right? So dq we're taking is the charge E and the dt is the time which is required to go from source to drain. So if you equate the expression here to this E by tau, we are getting 1 by tau is 2n d by h. 1 by tau, it is 2n d by h. Let me know up to this part if it is clear. Then I can move on to the next part. Okay, so we now got the expression for 1 by tau. So we can put the expression that we have taken in the first stage. So power is EVST by tau. So I've just put the value of 1 by tau here, and we need to calculate the total power dissipated. So that is why we have uh, taken the limit from mu L to mu R. And this is 2En VST by H. So these are constant. So that is why the integration now will get, so integration of dE will give a E value, and E is varying from mu L to mu R. So that means the integration will come out as mu L minus mu R, which is E times VST. So that means now you have a VST here, we have a VST here. So you have square of the voltage divided by, so I have rewrite this uh, value so that I can get a value of resistance. So I've just taken this 2Ne to this denominator. Okay, so V square ST by H to H by 2 E square N. And this power expression, it is similar to V square by R. So that means R is H by 2 E square N. So the contact resistance that we have seen in this 1D channel uh, in the 2D electron gas, this is the expression of H by 2 E square 1 by N. Okay, you can see the contact resistance is inversely proportional to the number of modes. And for the power, you can see the power is directly proportional to the square of the voltage, and also it is directly proportional to the number of modes that is available in the channel. So conceptually, if you want to understand it, so that is what I was trying to cover. Let me take a bigger one. Let us say we have a schematic like this, 2D electron gas, and we have made 1D quantum point contacts, and we have a source and drain here. So don't make a confusion that the contact resistance is the resistance that we see in source and the drain side. So this is not the case. The main contact resistance, why we are getting this value, is that in the quantum point contact region, in this region, we have confinement. So that is why we see 1D reflectionless channel here. But once this 1D channel leave this contact region, they enter this bulk part, which is 2D electron gas. So this will have a allowed levels, right? All right. And this bulk part, which is the 2D part, they will support many modes which are not supported by this 1D channel. So that is why when this 1D channel interacts with this 2D electron gas or the modes that is supported by this 2D electron gas, there will be a scattering, and because of that we see a non-zero resistance, which we call as a contact resistance. Okay, so this is what the overall uh, physics of getting finite resistance in the quantum point contact result. Okay, so let me know is the concept is clear or not, or otherwise we'll start solving problems for now. In the next part of the lecture, we have seen some of the application of this quantum point contact. We can use it as sensor or we can use it to trap the electron. So this has been covered in the class. So this is all the physics that I wanted to cover for today. For now, let us move to our problem solving part. Let me know before whether you have any doubt, or I can just move on to start solving the problem. In the previous lecture, we were left with some of the question from week 5. So let us try solving that first, and we'll move on to the week 6. Okay, so let us try to cover it in within, let's say, 15 minutes or 20 minutes. Then we'll see the question from week 6. Okay, so question number 7, we have, how does the weak localization change in the presence of strong spin orbit coupling when a magnetic field is applied? Option A, with the strong orbit coupling completely eliminates any field dependence of the conductivity. Option B, weak localization becomes independent of spin dynamics and remains unchanged. Option C, interference changes sign, leading to weak antilocalization and a low field negative magnetoresistance. Option D, the root conductivity becomes zero because of the spin orbit scattering. Stops all this transport. Which one of this, the following you think is the right answer for this? So you have a weak localization, but there is a strong spin orbit coupling in the presence of magnetic field. So if you recall, there will be anti-localization. Yes, option C is the correct. So we'll see that the conductance will now increase because the interference changes the sign. So there won't be any constructive interference. There will be destructive interference, and there is a lifting on weak localization. Okay, question number 8. For phi is phi 0 by 4. Which of these following correctly shows the relation between relative phase shift in the AB effect and in the ASS effect? So you need to calculate how del phi AB it is related to the del phi ASS, and also what is how this the periodicity of AB, how this is related to the periodicity of ASS. So it will take some time. So let me solve it. You can revise the concept. Okay, if not, if you have any doubt while I am solving it, please try to clarify it now. Okay. So in the AB effect, what do you mean by AB effect? So there will be a phase introduced whenever these two paths interfere with each other. So we have a current going through, it can take this L1 path and come to the, so this is J1 point, let's say this is J2 point. So the current can take the L1 path or it can take this L2 path. And we see that whenever these two path interfere, there is a phase difference, and because of this phase difference, we see a oscillation in the current. So del phi for the AV phase, this we have calculated by taking the vector potential. And if you recall, it is given by 2 pi phi by phi 0. Given pi is phi 0 by 4. So if you put it here, so this will be pi by 2. Okay. So phase shift for the AV phase is pi by 2. For the ASS effect, so ASS effect is the case where we have a, we consider that there is a return probability. Okay. So this is opposite to the AV effect. So we have the same case, but now whatever light is incident, it is getting to the original path. So we can have a two path, which is the time reverse path. This can be either clockwise or, let me take a different color. This is the anti-clockwise path. And for this ASS effect, this is 4 pi, pi by pi 0. So that means it will give a value of pi. Okay. So that means if we can compare this, so del phi ASS, it is 2 times of del phi AB. Okay. And now we need to see what is the periodicity. So periodicity we can get if you look at this relative phase shift. For ASS, if you see, sorry, for AB, it is 2 pi phi by phi 0, right? So this is the relative phase shift. So that means the phase, the current will repeat if if the phi is some integral multiple of phi 0, or the minimum separation is phi 0, right? If phi is phi 0, then it is 2 pi. So it is periodic. So that means the periodicity for what, sorry, for the AB effect, it is 2 pi. For ASS, if you see, it is 4 pi phi by phi 0. So that means if pi is phi 0 by 2, then this phase shift will become 2 pi, and the expression will, or the relation will repeat. So the minimum phase shift required to repeat the phase or to get the periodicity is 2 pi, right? For AB phase, 2 pi is already there. So that is why if you take the phi is phi 0, then the relation or the what is the graph, they will repeat. But for the AS effect, it is 4 pi. It is 2 times of 2 pi, right? So that is why if you even though if you take half of 50 by 2, then we'll get a 2 pi and the expression will repeat. So that is why the periodicity of AB, it is 2 times of periodicity of, sorry, this is phase, right? So periodicity of AB, it is 2 times of periodicity of ASS. So is this clear? Answer would be, you can easily see option C. Let me know whether the steps are clear or not. If not, I will try to cover it again, or otherwise we'll move to the next part. Okay. So question number 9. It's given for a diffusive loop with enclosed area. It is area given. There is a loop. Area is 0.25. It is placed in a magnetic field 0.05 Tesla. What is the magnetic field induced relative phase in radians between the time reverse path? So you need to calculate the magnetic field induced relative phase between the time reverse path. What do you think will be the answer for this? So formula is for, okay, let me solve it. Uh, the time reverse path, they have a phase shift of 4 pi by 50. This we have seen in this case also, here in the AS effect. So this is nothing but the phase difference between the time reverse path. One is clockwise, other one is anti-clockwise. So in this case, also we'll say get the same relation. It is 4 pi by 50. 50, if we recall, it is given by, it is the flux quantum. It is given by h by E. So the values are known to us. H is 6.63 into 10 to the minus 34, is 1.6 into 10 to the minus 90. So this will, you will get 4.14 10 to the minus 15 Tesla meter square. This is for 50. For phi nothing but B dot A, right? B is given, A is also given. Okay, I think the unit, okay, it's given unit of area is, this is 0.25 micrometer square. So that means B dot A will be, this is 0.05 into 0.25 10 to the minus 12 Tesla meter square. So now it's easy, del phi between the time reverse path, it is 4 pi by 50. And if you put it, it will come around 4 pi 3.02, which is 37.92 radians. Option B. Should I move to the next question? In the next question, we have a silicon MOSFET sample which shows a weak localization magnetoresistance, which is suppressed above B, which is equal to 4 millitesla. So the weak localization, it is suppressed above this magnetic field. That means this is the critical magnetic field. Okay, now the question is asking estimate the phase coherence length L5. And it is given that you can use 50 as this. So we need to calculate L5. So this is also a formula based. If you recall, BC, you can write it as 50 by L5 square. 50, it's this is known to us. BC is also given. That means L5 is, it is square of 50 by the critical magnetic field. So this is straightforward. You need to just put the values. 50 values is already given in the question. And the critical field is 4 millitesla. So this will give 1.035 to 10 to the minus 12. Or the value will be around 1.02 micrometer. Option C. Question number 11, it's a conceptual one. It's a given in a 2D weakly disorder metal, which experimental observable is most directly analyzed to extract the phase induced by a magnetic field on weak localization loops. The thermopower measured at zero magnetic field or the low field magnetoresistance delta sigma B is delta B minus delta 0, or option C, the optical reflectivity spectrum at room temperature. Option D, there is a zero field Hall coefficient as a function of carrier density. So for weakly designed metal, the experimental observable which is directly analyzed is option B. This is already given in the lecture. So you can calculate delta B. Okay, question number 12. It is also conceptual. What is the main role of phase coherence length L5 in determining weak localization and its separation by a magnetic field? Option A, it controls the strength of electron-photon coupling coefficient. Option B, it sets a scale over which electron density is uniform and it is independent of dephasing. Option C, it fixes the mean free path of elastic scattering events. Or option D, it determines the maximum size of the lobe that contribute coherently to the interference correction. Which one of these is correctly related to the phase coherence length? This is option D. Okay, so this is, so if you recall L5, it it defines the what will be the maximum size of the lobe so that weak localization can happen. So below, if the lobe phase size less than L5, then it's possible to see the weak localization. But if it is greater than L5, then there won't be any phase coherence. So that is why the weak localization will now break. So that means it sets the limit where maximum size of the loop can be determined, and depending on that, they will contribute coherently to the interference correction. So if it is showing weak localization, then there is a coherence correction. There is a quantum correction to the conductivity. Okay. Okay. Question number 13. It's also directly formula based. An electron of charge Q minus E travels along a path where the scalar potential is given Vt is V0 and it is constant in time during a time interval of duration T. What is the phase change acquired by the electron wave function solely due to this potential related to the free propagation? So phase change in the presence of a potential. If you recall delta phi, you can write it as minus q by h cut Vt dt. And it is given V0 and it is constant in time. So that means it is q V0 by h cut and dt, the duration is given, it is t. So that means delta, the phase shift is minus q V0 t by h cut. Or q is E. So I think option A will be the correct option. Yes. And A. Question number 14. So it is somewhat similar to question number 13. So you have two electron paths in a interferometer which are identical in length and experience no magnetic fields. Path A crosses through a region where the scalar potential is PAT is 0 for path A, and pathway passes through a region where VBT is V0 only in the middle third of the travel time. So this is non-zero for T0 by when time is it is middle third of this travel time. That means let's say if it is starting from 0, then it can go on to T by 3. And it is 0 otherwise. Okay. What is the relative phase shift delta phi at the output? We can use the same expression. Delta phi is q by h cut. Option C. Yes, you are correct. So that means you got the answer quickly. So you can use the above expression. The dt will be now t0 t by 3. Okay. So now let us solve what we have for week 6. Of question number 1, which one of these following is true for a quantum point contact? Option A, these are 1D ballistic points. These are 1D ballistic points in a two-dimensional semiconductor heterostructure. Option B, gate voltage controls the number of modes available for transport at the quantum point contact region. Option C, confinement effect of this charge carrier across the quantum point contact region can be observed at any temperature. Option D, none of them. Which one of this you think is the correct option? A and B. Yes, you are correct. So A and B are the correct option. Okay. Question number 2. According to the Landau formalism, the two terminal conductance of a ideal quantum point contact at low temperature and B equal to 0. What is the correct expression for conductance at low temperature and when there is no magnetic field? Yes, it's correct. So this will be 2 square by h because B is 0, so there will be a spin degeneracy of 2. Question number 3. In a gallium arsenide quantum point contact data at temperature 80 Kelvin, when B increases from 0 Tesla to 8 Tesla, new plateaus appear at integer multiple of 4 square by h, or each 2 square by h plateaus split into two steps of e square by h due to Zeeman splitting. Or option C, all quantization disappear. Option D, the conductance increases continuously without any steps. So which one of this correct for a gallium arsenide QPC when we increase the temperature, increase the magnetic field from 0 Tesla to 8 Tesla? Yes, option B is the correct because there will be a Zeeman splitting and there will be a plateaus will now split in steps of E square by H. Question number 4. In a bilayer graphene quantum point contact at 0 Tesla, the plateaus occur at multiples of E square by H, 4 E square by H, 2 E square by H, or 8 E square by H. For bilayer graphene. So if you recall, for the bilayer graphene, we have both spin degeneracy as well as the valley degeneracy. So spin degeneracy has a factor of 2. So up spin, down spin, and valley also there are two valleys which is the same energy. So now that means the plateaus will have a multiples of 4 e square by h. Okay, so this is because of the spin and valley degeneracy. Okay, question number 5. In metals, conductance quantization is observed only when the constriction width is 100 nanometer or larger. Option B, a strong magnetic field is applied. Option C, the channel width is reduced to atomic scale because lambda f is a fraction of nanometer. Option D, the temperature is raised above 300 Kelvin. Yes, this is correct. Lambda f is on the order of nanometer. And to see the quantum ballistic region where the quantization is happening, we have to have the channel width in the order of atomic dimension. Okay, question number 6. In a QPC, it shows exactly 4 conductance plateaus at a given density. What is the width of this constriction when lambda f is 50 nanometer? QPC means quantum point contact. So this I have written for short. This is quantum point contact. So you have a QPC which shows 4 conductance plateaus for a given density. So you need to calculate what is the width of this constriction when you have lambda f is 50 nanometer. And it's also saying there are 4 conductance plateaus. Yes. You have guessed the correct formula to be used. So that means number of modes, we have the relation number of modes, it is 2W by lambda f, right? Lambda f is given, W we want to calculate, N is also given because it's showing there are 4 conductance plateaus. That means the number of modes here is 4. So 4 is equal to 2W by lambda f. So W is 2 times lambda f. Lambda f is given 50 nanometer. So that means it is 100 nanometer. So construction width will be option B, 100 nanometer. Option B. So is it clear? Okay, question number 7. Which of this following is not true for 1D system? For 1D, the density of states, it is directly proportional to square root of E, and the group velocity is inversely proportional to 1 by square root of E. Or the states at higher energy are less populated, but they move faster. States at lower energy are more populated, but they move slower. Or option D, the group velocity is inversely proportional to the density of state. So which of this following is not true for 1D system? So question asks which one of this following is not true for a 1D system. And if you recall, for 1D, the density of states, it is inversely proportional to square root of A, right? For 1D. For 2D, if you recall, it is a constant. And for 3D, it is directly proportional to square root of A. And 1D, we have 1 by square root of A. And for 0D, it is like a delta function. So this you should keep it in your mind. What is the density of states relation? For 1D case, we have a 1 by square root of E. And the group velocity, it is for 1D, it is directly proportional to square root of E. This we can get it by taking d omega by dk. Okay. So that means the first term, it is not true. This is this is one of the answer to the question that the question is asking about, that which of this following is not true. That means this is not correct. Let us see option B. Option B says states at higher energy are less populated, but they move faster. So let us see the energy of higher state. If we see the relation here, the density of states is inversely proportional to square root of V. That means if the energy increases, that means if we are moving to the higher energy levels, then the density of state will decrease. So density of states will decrease means we say that these states are less populated. But if you look at the group velocity relation, when the energy increases, the group velocity is also increases. So this is what we mean that if you go to higher states, these states are less populated, but they move faster. So that means this option is also correct. States at higher energy are less populated, but they move faster. Option C, let us see whether it is true or not. It says states at lower energy are more populated, but they move slower. This is also obvious from this relation. So when the energy will now decrease, the density of state will increase. That means more states are there. So the states at lower energy, these are more populated, which is also written here. But the group velocity will now decrease because these are low state. So that means this is also a correct for 1D case. And option D, the group velocity and density of states are inverse related, which is also true. So that means the correct option, which is not true for the 1D case, is option A. Okay, so this we have also seen in the lecture when we are trying to calculate the current. So when we try to calculate the current, the Vg cancels. It is because they have a inverse relation. Okay, Vg cancel with the density of states. So is it clear? Okay, question number 8. Okay, I think it's almost time. So we'll start from question number 8 in our next lab session. Before that, let me ask whether you have any doubts in any of this question that I have explained. Okay. Okay, then we will stop for today. Thank you for joining the session. I hope the problems that I have solved and the concept that I've covered, it is clear to you. And we will meet on next Friday, same time from 6 to 8 to solve more problems for week 7, as well as the problem from week 6. And yes, I will write to them by today for your doubts for the assignment. Please don't worry, just wait for 2 more days. If I get a reply, then they will surely address the issue as soon as possible. Okay. Okay. So thank you for joining the session. For now, let us meet on next Friday. So bye everyone.